Today we're going to talk about the concept of statics and torque. And first we need to define what statics is and what static equilibrium is. And so this person, because they're not moving, is in what's known as static equilibrium. So first of all, statics is the study of force in equilibrium. Now, when force is in equilibrium, then the net force is equal to zero. And the net force not only is overall is equal to zero, but the net x component of that force and the net y component of that force is also equal to zero. So in this motionless person, you have a situation of static equilibrium. All the forces that act on him add up to zero. In this case, there are only vertical forces. So you have W, which is shown in this free body diagram here. So you have W down and the normal force up. Those two are in equilibrium, so the net y component and the net total is equal to zero. Now here's a second situation. The first person is an example of a static situation where there's no motion. You can also have a static situation in which there's constant velocity. Because remember, if there's any force being exerted, this force would result by Newton's first law in an acceleration. So if you have a situation of constant velocity, you also have a situation of static equilibrium. In this case, there are both horizontal and vertical forces, but the net external force in any direction is equal to zero. This free body diagram shows that you have four normal forces, each normal force acting on each tire, and they are counterbalanced by the weight of the car. Similarly, the applied force that keeps the car moving forward is counterbalanced by the friction and air resistance, shown here as little f. So all of these are balanced, so the upward force and the downward forces added together add up to zero, and the forces to the left and the forces to the right add up to zero. So this also is a static equilibrium, even though the car is moving at a constant velocity. Here's another case where you have a hockey stick. You have a hockey stick that's lying flat on the ice, and there are two equal and opposite horizontal forces applied to it. The friction here is negligible, and the gravitational force is balanced by the support of the ice. So you have both the normal of the ice and the gravitational force of the weight of the hockey stick. Again, the net is equal to zero, and you have an equilibrium and it's a static equilibrium in this case. Now, in a non-equilibrium, it occurs when rotation occurs, leading to a rotation of the stick. Here the same forces that were previously applied, shown here, are applied, but now they're not applied directly across from each other. And because of that imbalance of where they're applied, you have a net accelerating rotational force. So you have a net of zero because these two are in opposite directions and they're equal. But because they're not applied directly across from each other, the system itself is not in equilibrium. Therefore, the idea that the net forces are zero is unnecessary but not sufficient. Other factors, such as the placement of where the forces are, can cause the lack of equilibrium. So you have to have not only F net equals to zero, but you also have to have other factors to be true before you have a condition of equilibrium. Now the second concept that we want to look at is the concept of torque. And torque is the turning or twisting effectiveness of a force. Here it's illustrated by the rotation of the door on a hinge. And this is viewed from above. Torque has both a magnitude and a direction. And torque is commonly abbreviated small lowercase t or lowercase tau. Here you have force, and it's a force times distance is the torque, and it's the perpendicular distance. So the torque is the force, this force times this distance, and it's generally in the direction of the force. And this is just examples that you can change the torque by changing the force applied at the same distance, or you can change the torque by keeping the force the same but changing the distance. Now, if a force is applied to an object that produces a torque, what the torque is depends on the pivot point. That is, we have a force here with a pivot point here, and a force here with a pivot point up here. And the torque may be different, and its result may be different depending on where the pivot point is. And it's true that even in this situation where you have the R perpendicular being the same, these two torques are not the same because they result in different motion. So 3 factors affect torque: the distance between the pivot point, the perpendicular distance between the pivot point and the applied force itself, and then this angle theta, which is the difference between a line drawn from the pivot point to the where the force is applied, and the parallel line to the force that's applied. So this is theta right here. In this case, one results in counterclockwise motion, the other results in clockwise motion. And it's all because the pivot point has changed. The other things are the same. Now here we have 2 individuals sitting on a seesaw, and the seesaw does not move. The units for torque are Newton meters because it's a multiplication of distance and force, okay? And you have a smaller person with a larger distance from the pivot point versus a larger person with a smaller distance to the pivot point. And these two products, R1 times W1, has to equal R2 times W2 in order for this to not to move. Also, the upward force, FP, that holds the seesaw in place has to be equal to the sum of the 2 weights, and that is shown here. Equilibrium requires that the net torque is equal to 0. So the net combination of this plus this has to equal to 0. So you have 2 children balanced on a seesaw, and they satisfy both conditions of equilibrium, in that the torque is equal to 0 and the weight is balanced by the upward force FP. This child has to be sitting farther from the pivot point because he's smaller than this child. So if we look at a problem and put some numbers in here, you have 2 children balanced, and the first child weighs 26 kilos and sits 1.6 meters from the pivot point. The second child has a mass of 32 kilos, so this is the bigger child. How far would she have to sit from the pivot point? And then the second question is, what is FP? Well, if we look at this, first of all, because the sum of these has to equal 0, they have to equal each other. And for this to be in equilibrium, the total torque has to equal 0. So R1 times W1, which is the torque caused by the first child, is equal to R2 times W2, and then that equals 0. So these two are equal to each other. The second condition is that the weight of the 2 children together have to equal the upward force on the pivot point. And here we have it with numbers. I've scrambled this around so that we solved for R2, so that's equal to R1 W1 divided by W2. So we have 26 is the weight of the boy times 9.8 meters per second squared, gravity, times 1.6 meters, that's how far he is from the pivot point, divided by her weight, which is 32 times 9.8. And if you do the math here, you get 1.3 meters is the distance R2, which is this first question. The second question is the sum of their weights is equal to the upward force, and if you add their 2 masses and multiply that by gravity, you get 568 newtons as the upward force on the pivot point. Now here's another problem. What is the force on each of 10 braces? So this shows on the side 1 of 10 braces. Here's one of them. If a strong wind exerts a horizontal force of 650 newtons on each square meter of the wall is 11 meters wide. So you have a wall that's 17 meters tall and 11 meters wide. So its total area is 17 times 11. And each square meter of the wall has 650 newtons on it. So if we look at that, the force of the wind is going to be 650 times the area of the wall, or 1.21 times 10 to the 5th newtons. Now, this has to be held up by these 10 braces. Okay, so you have the force or the torque caused by the wind, and that's the force of the wind, and here's the pivot point for the distance. That some of it's up here, some of it's down here, but the average is this distance. So it's going to be times 8.5 meters. That has to equal 10 times the distance of the brace, which is here, times the sine, because it's only the x component of that force, the sine of 35 degrees. So whatever the force of this is, it's going to be times 35 degrees, because some of the force is in the y component, it's pushing up on the wall, and the other is pushing this way. And only the sine component is part that we're looking for. And if you do the math here, you get 2.12 times 10 to the 4th newtons. Here's another situation, and we're going to turn now to the concept of stability. And a system can either be stable, unstable, or neutral. And the definition of a stable system is where an equilibrium where if the system is displaced, it experiences a net force and torque in the direction opposite the displacement. So in this case, if we push the pencil to the left, then if it's stable, it will experience a force and torque to the right in the opposite direction to bring it back to where it was. So a stable situation, if the pencil is displaced slightly to the left or clockwise, it's not in equilibrium. Its weight produces a clockwise torque, which is in the opposite direction, and that returns the pencil to its equilibrium position. Now conversely, an unstable equilibrium, if you displace the system in a certain direction, then the torque and displacement that occurs after that displacement is in the same direction. So if you're pushing it to the left, and if it becomes unstable, it will continue to, the torque and force will continue to the left until it falls over on its side. So if the pencil is displaced too far, the torque caused by its weight changes from a clockwise direction to a counterclockwise direction and causes the displacement to increase instead of decreasing. Now the third is neutral, and this is a system where it's independent of the displacement. In other words, it doesn't matter what the displacement is. And here's an example of a neutral. In a neutral situation, we have the center of gravity of a sphere here, and it lies directly over the supporting normal that holds it in place. Now, if you displace this, nothing really happens. It's still, the orientation of the force, the weight, and the normal remain the same. And so this is an equilibrium that's this is a system that's in equilibrium in any location, and then if displaced, it doesn't move or it doesn't experience a correcting force. Now, if you're looking at a pencil according to its cross-section, it acts in a similar way. It's also neutral and independent of displacements. If you're looking at it from a cross-sectional, circular cross-section. We're going to end right there. When we come back, we're going to talk about this little guy right here and how you solve problems with this guy.